Hello everyone, I'm Byungsoo. Thanks for coming to my talk. Today, I'd like to present our paper, Deep Reconstruction of 3D Smoke Densities from Artist Sketches. Filmmakers and video creators often use storyboards to transfer ideas from their mind to the screen. And this is a very interesting example. In pre-production of Raiders of the Lost Ark, Steven Spielberg asked illustrator Ed Ferrox to draw storyboards for the climax of the film. And see how closely they guided the final film imagery. We see the great use of sketch and shading in storyboards to represent a mysterious energy stream around. But they are used for the purpose of communication rather than a final visual realization of 3D flow. So the natural question is, can we transfer these concept sketches directly into 3D volumetric flow structures? Traditionally, modeling density volume is performed by detail synthesis on coarse shapes. Once a guide mesh or sketch is given, then texture or noise is procedurally synthesized to fill out the guide with high-frequency details as a post-processing or during rendering time. These methods are, however, limited to capture intrinsic flow details in the modeling step. Therefore, we present the first method to compute a 3D smoke density field directly from 2D hand-drawn sketches. In our method, we aim to reconstruct smoke density fields from shading-based artist sketches in order to integrate flow structures already in the modeling step. The main purpose is to bridge the gap between early-stage prototyping of smoke keyframes and visual realization. Notice that although 3D smoke reconstruction from 2D sketches is heavily under-constrained, our method gives plausible results. Again, such a sketch-based reconstruction is an ill-posed problem due to the sparsity of sketch data and the ambiguity when inferring another dimension. Previous work indicate that the use of convolutional neural networks is especially powerful in such tasks. To the best of our knowledge, our work is the first learning-based sketch method for turbulent density volume reconstruction. Another interesting direction parallel to our work is fluid reconstruction and editing. For instance, 3D fluid densities and motion have been reconstructed from image sequences, and sketches have been used to control the motion of liquids or 2D flow field generation. All right, so before talking about details of our method, I'd like to explain our fluid sketch principle. Sketches are the primary control tool for the artist during the authoring process. And sketching fluids requires a specific style and workflow, so here we summarize the style decision. Firstly, our target is chaotic nature system, so we don't impose any geometric constraint on structure. Secondly, according to the design principle of effects drawing, we keep it simple without random details while still keeping its generality. Thirdly, our style is made of several strokes with varying shading and thickness, similar to many other modeling techniques. Lastly, to express the variations of the curvature of smoke objects, we impose a two-color tone shading with a light source. And this is our final guideline about strokes and shading for sketching fluids. And we'll see how artists took advantage of our sketchy style for drawing later. One major challenge of sketch-based modeling lies in the depth ambiguity and occlusions that cannot be captured from a single viewpoint. Thus, we progressively refine sketches at different angles inspired by Delanoy et al., and hence iteratively update and relocate smoke structures. Finally, our method delivers two key properties while authoring. First, the output density volume seen from target view should correspond to the input sketch. Second, the occluded part of density volume must be preserved to ensure multi-view continuity. So let's go over our pipeline. We propose a simple method called initial volume modeling to create an initial guess from two sketches in canonical views. The basic idea is to extract contours and foreground to compute a visual hull of given object. And at test time, the updated network takes a pair of sketch and density volume as input and computes a residual to correct the volume. By rotating to an arbitrary viewpoint, the result can be iteratively refined. At the end, a subsequent post-processing GAN synthesizes additional fine structures. At training time, we use a semi-supervised training strategy to enforce two key properties already detailed. The single accuracy and multi-view stability are well targeted by our carefully designed loss functions. The key ingredient is our novel synthetic sketcher for smoke volumes, producing sketches that are compliant with our sketch guidelines. Here we show the output of the individual passes at test time. We compute the initial volume and then alternatively optimize the front view, left view, front view, and left view again on density reconstructions with our updater. The intermediate density reconstructions and corresponding sketch representations illustrate the convergence after multiple passes. We found that two subsequent refinement steps already show decent quality of convergence. Let's move on to our loss functions. In each pass, we calculate view-dependent losses. First, density loss compares the reconstructed volume with the ground truth, and sketch loss compares their corresponding sketch representations. Depth variation loss is additionally designed to suppress the depth ambiguity from sketch loss. Lastly, our full objective is defined to preserve reconstructions of all input viewpoints. We evaluated the impact of the different loss functions and illustrate the results. Baseline is only with density loss. We see there is no detail preserved. And if we use only sketch loss, we see very detailed result like this, but at the cost of depth ambiguity. If both density and sketch losses are combined, the result looks good as sketches, but there are still some artifacts in the depth axis. Finally, depth variation loss is added. Our result looks quite close to the input sketches while reconstructing plausible volumes. Another study on multi-view stabilities. We trained the network on different number of passes and evaluated the quality of convergence while refining on the same viewpoint. Training with a single pass shows lots of dissipation over updates. With two passes, it shows much better convergence, but still losing its stability over iterations. From 3 passes, we see our method achieved multi-view stability, and we use these 3 passes in practice. Coming back to the pipeline, I would like to go over our sketch generator, which is at the core of our method. Our differentiable sketcher allows us to automatically annotate smoke data without necessity of storing, and to directly incorporate it into the loss functions during training. And these are great advantages to secure the stability and robustness of the model eventually. Previous techniques typically extract contours from meshes and cannot be directly applied to amorphous shapes such as smoke densities. Although isosurfaces can be extracted from the density grid and converted into a mesh as seen in the left image, the choice of ISO value is not obvious, and typically low density details are lost in the process. Meanwhile, for cartoon rendering of smoke, particles have been used and traced through the underlying fluid grid and then rendered as textured billboards. Both methods, however, do not work directly on volumetric data. Our differentiable sketcher generates corresponding sketches on the fly for the end-to-end training. Our method is inspired by the absorption in a smoke rendering and estimates a normal map. We average normals for a range of density isosurfaces at the visible boundary of the smoke. Then contours are extracted, followed by two-color tune shading to provide more information about volumes. We combine those to compute a sketch finally. Thanks to our lightweight sketcher, we can create an infinite number of variations in sketch style to increase the robustness of our model during training. We augmented the sketches for brightness, contrast, contour strength, tone shading color, blurring, slurring, and different light directions. At the end of our refinement, we use a second network to synthesize flow details onto the reconstructed density. This will help artists alleviate the necessity of drawing small-scale structures, which is to enforce simplicity, one of our fluid sketch principles. We use the architecture of multipath GAN without using temporal discriminator, as we focus on individual keyframe without taking care of temporal consistency. This model requires an underlying velocity field in addition to the density field, so we created synthetic flow field using current noise at test time. Note that it also gives us controllability by parameters. The generality of our dataset plays an important role for robust and high-quality reconstruction of diverse scenes sketched by artists. Those sketches can include both physically inspired and non-physical shapes and motions of smoke. And therefore, we build a new dataset consisting of smoke densities, which captures a large variety of volumetric shapes. They mainly categorize into two types, with and without density source, as seen in the video. Based on the density histogram, we find that both simulation strategies are complementary to each other. We run the simulation in Houdini with randomly changing temperature, diffusion factor, cooling rate, viscosity, and so on. This comes along with the sketch augmentation technique for increasing robustness of our model. So right, here we show the reconstruction result of training data. Top row shows front view, and bottom row shows left view. From left to right, we see input sketches and our sketches from reconstructed volumes and ground truth. Only minimal differences are visible between input sketches and the sketches of our output. And we see the reconstruction result of unseen data and during training. And still, we see only subtle differences in sketches. Note that the reconstructed density is smoother than the ground truth. This is because the sketch lacks complete information about the original density and implies the ambiguity of several possible densities corresponding to a given sketch. While an alternative could be to use a sketchy style that also encodes fine flow structures, but we prefer to follow our sketching principles and to synthesize high frequency details in the post-processing. We show that our method generalizes well to various scenes. First, we tested our model on data from physics-based simulations. Front and left sketches are generated using our sketcher. The reconstructed density closely matches to the footprint of input sketch. We measure the quality of inner details by comparing input sketches with ours, where we see that the shading and inner contours are well captured. Note that the given density cannot be directly compared to the reconstructed density, as our updater focuses on low and mid-level frequencies to be close to the input sketch. Another interesting test case is non-smoke shapes. We selected some frames from animation sequences. Note that these are difficult cases for our model, as they show thin extremities or occlusion, and there was no comparable examples in our training dataset. Nonetheless, differences between sketches are still minimal, demonstrating that our method is not only able to reliably reconstruct unseen shapes, but especially also handle non-physical inputs. Finally, we demonstrate our approach on 3 real-world applications. We first present 3D smoke results using sketches from multiple different artists. We instructed the artist to sketch keyframes of smoke or an imaginary smoke-like object. Our method works surprisingly well for such highly non-physical examples. The reconstructed density and sketches closely match the input sketches from the artists. Note that the reconstruction is also robust to variations from the prescribed sketches style and can handle inconsistencies of shape and shading between the different views. As a second application, we implemented the Houdini plugin for interactive smoke field authoring. Here we show selected sessions. It took the novice users only a couple of minutes to create, edit, and render the final widgets. Interestingly, our sketcher provides them with an estimate of sketches as guidance from unseen viewpoints. We can see many imperfections, such as not corresponding front and side input sketches, sketchy style differences, or gap between strokes. Even in such challenging cases, our method could reliably infer the 3D shapes. Let's have a look at some results. As a last application of our method, author smoke keyframes can be used for target-driven fluid simulations. We used 2 reconstructed frames from sketches, and the resulting animation showed that the simulation matches the target density keyframes, while generating intrinsic flow structures due to the dynamics by underlying physics solver. As one part of evaluations, we compared our results with those of Stever et al., which is surface-based modeling followed by filling with noise particles. The results indicate that our approach can reconstruct intrinsic flow details more realistically than counterparts. We also demonstrated user study to evaluate our results with respect to overall similarity, outer and inner contours, shading, and similarity to the real smoke structures. Overall, our method clearly outperforms the previous work, except for one reality question. Additional study with users of authoring tools also implied that our tool is useful for early stage prototyping, and also they're satisfied with the quality of features, and sketching style was intuitive. So in sum, we propose a method for the real-time and a iterative refinement method for small volumes from sketches. Also, it includes differentiable sketch generator with fluid sketch principles. We also suggested carefully designed loss functions, dataset, and augmentation technique for a robust model. And we suggested 3 demo applications like artist sketch test, interactive authoring, and smoke target-driven animation control. Our method have some still limitations and room for improvement. For instance, our method is limited to unscalable and simplified sketch representations and density representations. And we couldn't really also handle the arbitrary drawing styles from the different artists. So that's all from my side. Thanks for your listening.